Like I said, happy Friday, everybody. Thanks for tuning in today. This week, our seminar speaker is Dr. Jennifer Whitten, who is currently an assistant professor at Tulane University in New Orleans. Dr. Whitten is a planetary scientist whose research focuses on understanding the processes that generate and modify the crusts of planetary bodies. Her research is quite diverse, spanning not only different topics, but also planetary bodies, from studying volcanism on the moon to using radar to study the south polar layered deposits on Mars. She received a bachelor's degree in geology and art history from the College of William and Mary in Virginia, and a master's and PhD in planetary science from Brown University. After that, she did a postdoc at the Smithsonian for several years before starting her current position at Tulane. And she's also involved in several missions, including her most recent role as Associate Deputy PI of Veritas, which is an upcoming mission to Venus. And I think today we are hearing about Venus and hopefully a little bit about Veritas. And so thanks again, Dr. Whitten, for taking the time to talk with us. Take it away.
Thank you for that introduction. I'm really pleased to be here today. I am very excited about Venus right now. I think the whole planetary community, well, that might be a bit of an exaggeration, but I'm very excited. You should have, we just had our major planetary conference a couple weeks ago, and we had a full day of Venus talks, which was the first time that happened in years. And so there's a lot of celebrating. And today I'm going to get to talk to you a little bit about some of my research looking at the surface of Venus, and in particular, studying a material called tessera, and they have been likened to Earth's continent. So I'll get into that a little bit here in the next couple of slides. Before I get too far into just talking about Venus, though, I'd like to take a second and provide a fuller view of a comparison between Venus, which is on the left here, and Earth, which is on the right. Oftentimes, Venus is called Earth's twin. You might even hear Earth's evil twin. I'm really trying to change that. It's a dramatic twin maybe, but not an evil twin by any means. The two planets are approximately the same size. They have about the same density and the same composition. There are some things about them, though, that are vastly different from one another, as evidenced by this image here. But in addition to that, the length of the day on Venus is about 243 Earth days. And its year is 225 Earth days. So its day is longer than its year. It also has a very different atmospheric composition from Earth. So it's dominated by CO2, about 95%. The surface temperature is quite warm. So it is hot enough to melt lead with an average surface temperature of around 730 Kelvin. And the surface pressure is around 92 bar. So a little bit hotter and a little bit higher pressure than on the surface of Earth. So a bit more uncomfortable, but still really fascinating planetary body. And as I mentioned, I'm going to be talking about what people have called Venus's continent. And so this is a comic that I really enjoy. It's XKCD comic. For those of you who aren't familiar, you should go check it out. Lots of funny science topics. But here we're looking at space without the space. So these are all of the solid planetary surfaces in our solar system. And you can see that we have Earth over here, and then we have Venus, and they're very similar in size. And what I've added to this comic is actually this sort of orangey tan color, which are the tessera of Venus. And these materials cover approximately 8% of the surface, I'm being a little generous there, which is a bit different in terms of ratio, but to give you a better sense for the topographic distribution of low-lying materials and high-standing materials on Venus, I'll show you a comparison of the topography between Earth and Venus. So on the top here we have Earth. I think we're all quite familiar with terrestrial topography. We have our ocean basins, which are our topographic lows, and our topographic highs tend to be associated with the continents. On the bottom here, showing Venus, and it does have this somewhat bimodal distribution where the low-lying plains, as they're called, which are interpreted as basaltic plains, have this, let's say, teal to purpley color. And the continental materials, the tessera, have these reds and yellows and even a little bit of green in terms of their topography here. And they're concentrated sort of predominantly in the northern hemisphere. So here's just that side-by-side comparison of Earth and Venus. And I'm actually going to slice through the interior because we know that if we study the continents on Earth, we understand something about the internal dynamics of Earth. And many people believe that we can study tessera and learn something more about the internal dynamics of Venus. But what is maybe interesting or surprising is that we don't actually know a lot about the internal structure of Venus. So we're very familiar with Earth and the crust and the mantle, and we have the inner and outer core. And based on the fact that Venus has a similar bulk density and bulk composition, we've inferred what the interior structure of Venus is like, and we have some planetary scale measurements of the internal structure, but it's really not nearly as detailed a picture as we have for Earth. But we envision that the abundance of radioactive elements between these two planetary bodies is relatively similar, so the amount of activity might be expected to be similar as well. And Venus is known as a very volcanically active body, but it's really missing the evidence of plate tectonics as seen on Earth, although there are suggestions of a flavor of plate tectonics on Venus. Okay, so how do planets get rid of their heat? This is a diagram that I've seen kind of many permutations of, but we typically think of three major ways that planets can release their heat. Thinking at the top here, this is Io. This is the most volcanically active body in our solar system, the moon of Jupiter, one of the Galilean satellites. And it has a heat pipe tectonic regime where you can have heat that's traveling from deep within the mantle straight up to the surface and exiting out via one of many of the volcanic constructs that we see on the surface of Io. A stagnant lid, which is where we think Mars is, where it's one solid lithospheric plate. And then we have Earth down here on the bottom left, which is our mobile lid, and that's the fractured lithospheric plates that are part of the plate tectonics process that we observe on Earth. And so given Venus's similarity to Earth, given its size, the question has always been, where does Venus fit here? We have been able to observe many things about the surface, including its age and geologic landforms. And so oftentimes Venus has been placed somewhere in between a mobile lid or a stagnant lid regime, or it has been suggested to bounce between the two. So at certain times in its past, Venus has experienced a more stagnant lid regime, and in other times it has experienced something similar to the plate tectonics on Earth, where you have heat escaping through this fractured lithosphere. And I think one of the really exciting things is initially people thought Venus had plate tectonics in the 90s before one of NASA's major missions to Venus arrived. People were speculating about all sorts of mid-ocean ridge type structures that they were observing and the available radar data. And then the mission got there. They didn't see what they were expecting to see. But recently there's been this resurgence and the idea that there is crustal resurfacing. It's just not exactly like what we're seeing on Earth. And so there's been many people who have suggested that subduction has been and is currently occurring on Venus. So this is a set of figures, and this is a movie. I'll get it running here in a second, where this is a physical experiment This is showing a surface, and this is the kind of mantle of this physical experiment. And what you're going to see very generally, which is diagrammed down here on the left, is material rising, impinging on the surface, akin to what you might think of mantle plume doing. And that as that process continues, the crust surrounding that plume actually starts to subduct or submerge into the mantle before detaching and sinking into it. So that's what you'll see here. This crustal material start to fall down and eventually detach and completely merge with the mantle materials. And so many people see these unique features on Venus called corona. And I have an example of Verdandi corona down here in the bottom right. And this is one of these corona. They're tectonovolcanic structures. They have often radial and circumferential fracturing. This one is not the best example, but oftentimes they are associated with volcanic domes and cones, either in their interiors or lava flows that are emanating from some of these concentric or radial fractures. And it's thought that these corona might actually be the areas of subduction where you have mantle plumes impinging on the surface and that you have material subducting around the periphery of these. And people have been looking at the available topographic data and gravity data, as well as looking at these physical models to infer this flavor of subduction, I'll say. So for Venus, it appears that subduction can initiate, but it doesn't persist for long periods of time. We also know that the volcanic record is suggesting that activity is pretty long-lived, and it may still be occurring today. There's been, I don't talk a lot about it in this talk, but there's been all these tantalizing observations over the last 30 years that are indicating active volcanism on Venus, but we have yet to kind of get that observation of the surface that 100% confirms that. And what we know is that the surface of Venus is very, very young. And so the hypothesis there is that within the last billion years, which I guess planetary scientists, that might be quite young, but maybe for other people, not so young. But Venus has experienced near global resurfacing through some mechanism, either an instantaneous resurfacing or a resurfacing that has occurred over a short period of time. And to give you a sense for the age of the surface, oftentimes in planetary science, we use the density of impact craters to infer age. And so the number of craters per unit area can give you an indication of how old the surface is. This is a view of Venus. This is Venus with a different topographic color bar, so I apologize if that's confusing. But what you see is there's about 1,000 craters, and that's kind of being generous. We're around like 990 impact craters that have been identified on Venus. And for comparison, these are the impact craters that we observe on the moon. Vastly different. We know that the surfaces of the moon have a variety of different ages, going from sort of, in some places, about 4 billion years old to places on the near side. This is the near side mare, with many fewer craters, maybe on the order of 2 billion years or 1.5 billion years for particular lava flows. I think the moon really provides a great example of this, that where there has been volcanic resurfacing, you expect a much lower density of craters because all of those old craters have been erased by that resurfacing process. So then the question for Venus becomes, I kind of alluded to this a few slides ago, but what type of resurfacing has occurred? And there are two end members to this debate, although there are many additional hypotheses. But one is that we have a catastrophic resurfacing event. That's shown on this bottom left graph. where you just have one major near global or global event that is resulting in the complete removal of impact craters from the surface. The alternative is that you have something called equilibrium resurfacing, where rather than every portion of the surface being resurfaced at once, you have frequent and small eruptive events that are occurring sort of near globally and are closely spaced in time, so that you can also have a near complete removal of impact craters. That's shown here, smaller but more frequent eruptions. So with Venus, there's a lot going on. A lot of it's pretty new. I said that the tessera cover about 8% of the surface. And so it's around, 90% of the surface are these low-lying plains that have been inferred to be basaltic. And so, as I said, I'm really interested in those tessera because we think they're older, although the crater statistics are not great. But stratigraphically, it appears that they're older, at least locally. And so they represent the oldest geologic record for Venus. And of particular interest to many people is what record of climate is preserved in those tessera. And this is a graph that is showing a comparison of the terrestrial planetary bodies, so Mercury, Venus, Earth, and Mars. On the y-axis here, we have time, where 4 billion years ago is near the top, and present day is near the bottom. Each of these planetary bodies has 3 colored bars associated with them. A deep blue that is a liquid surface water being present, a green, which is talking about the conditions that may be favorable for life, and then a red, which is showing the presence of active volcanism and tectonism. And I've highlighted Venus here because the really exciting thing, this is a very active debate. People definitely don't agree on this. So I do want to qualify this slide with that statement. But there have been some people who've been conducting climate models that suggest liquid water may have been present on the surface of Venus for billions of years. And that it's just oceans worth of water has recently disappeared within the last billion years. Now, what makes that exciting is that we think of Mars as this water world, but Mars, may not have had liquid water present on its surface for that long, although water has played an important role for a very long time. So this got everybody really excited, and for the tessera in particular, it begs the question, did they form in a different climate regime if they're some of the oldest materials, and is there a record of that climate preserved in those? I always like to kind of show this slide about geodynamics, and it's become very important. This is actually from an astrobiology report. I believe it was 2015. And what they show is that the geodynamics are really important for linking planetary interiors, surfaces, and atmospheres. So you're looking at that exchange of volatiles between each of these reservoirs as kind of the geodynamics of the planet play out. And so for me in particular, this is very interesting because it's directly related to this Veritas mission, which I am now a part of, that Francis nicely alluded to here. So I'm going to spend a few minutes before I get into my specific research. I want to just talk to you all about the Veritas mission. So Veritas is an orbital mission that is going to spend around 3 or 4 years orbiting Venus. The PI, the principal investigator of the mission, is Suze Mrekar, and Darby Dyer is deputy PI. I'm the associate deputy PI, and then we have project scientists. I won't get too much into that structure, but if anybody's interested, I'm happy to talk about mission structures as well. But the goals of this mission are sorted into 3 major categories. It's looking for evidence of past and present water, identifying evidence for current activity, and that can be in the form of weathering, aeolian, volcanic, or tectonic activity. And the last goal really is to determine the processes that shape rocky planet interiors. So those are our broad goals. As an example of more specific questions we hope to address are shown here on the right-hand side of the slide. So for the tessera, we really want to know their rock type and whether or not their rock type may indicate the presence of water. And in particular, people want to know if these materials have a basaltic signature or a granitic or other more silicic rock signature. For the volcanic history, again, kind of reiterating what I talked about before, which is, can we tell if the volcanism was steady or catastrophic, and how that is related to plate tectonics. Of course, people are very interested in this question of subduction. There's been a flurry of papers that have come out proposing these corona as sites of subduction, and some claiming they may be active today. But we're also very interested in the deep interior and constraining the interior structure, including the size of the core. But other questions include using measurements of the lithosphere to derive a global flow, and kind of using that to understand better why Venus doesn't have Earth-like plate tectonics. So next we have two instruments, but kind of three major measurement campaigns. So I'll just introduce you to those very briefly here. So we have a measurement campaign, which is our gravity science. And so what's really exciting about this is that we're going to get near uniform global coverage. And it's going to be at a higher spatial resolution with higher accuracy than our previous data sets. And so over here on the right-hand side, I'm showing you the gravity data as measured from the Magellan mission, which was a NASA mission that orbited Venus in the early 90s. And the degree strength is referring to how well we can resolve short wavelength variations in gravity on planetary bodies here. And so you can see that Veritas plots well over to the right here. And we've been doing some modeling, which indicates to us that we're going to get 2 to 3 times better data than the Magellan mission. So that's very exciting. The next instrument is really going to be a major workhorse for this mission. So it's the Visar instrument, which for those of you familiar with NASA, all of this is an acronym. So Visar is just referring to the fact that this is an interferometric synthetic aperture radar, and it will be collecting 3 data sets for us. The first is synthetic aperture radar imagery at 30 meters resolution globally. And that's very exciting because the current data we have is about 150 meters, but then processed down to a resolution of around 75 meters per pixel. Topography, I think everybody is excited about topography. The geophysicists, the mineralogists, everybody wants this topography. So the current data that we have for topographic data, again, was collected from the Magellan mission. An example of the Big Island of Hawaii is shown at the topographic resolution of the Magellan data set. And then over here to the left is what the data would look like in Veritas with this 250 meter posting resolution. So we're going to get significantly better resolution. And this is very important because we know that temperature changes as a function of altitude on Venus. And so we have kind of large scale views of how temperature changes and how that's associated with radiophysical properties of the surface. But here we're going to get a much more detailed look and be able to associate that more closely with certain geologic processes. And then the last thing, which is also very exciting, we're going to be doing surface deformation measurements, so INSAR measurements, where we look at large regions and we try and see if the surface has been deformed. So the idea would be to go to regions that we think are tectonically or volcanically active and target those for these surface deformation measurements. So for that topography, that's 2 orders of magnitude improvement. Mention that. And then lastly, there has been over the last decade this push to really develop the field of Venus spectroscopy. And so for this mission, we have the VEM instrument, which is the Venus Emissivity Mapper. And our goal is to determine global rock type and search for active volcanism. And so this is all data or measurement bands that are concentrated around the 1 micron region of the electromagnetic spectrum. Okay, so that's the Veritas mission. And the goal is to understand the relationship between tessera and ancient climate. But we don't have those data yet, so I can't quite ask those questions. So here on this slide, I'm showing you the list of questions that I can answer with the data that are currently available to me. And so this top bullet, are tessera significantly different from one another? This is a major thrust of my research, and I'm approaching this from 2 different perspectives. The first is looking at variations in radar properties, which is what I'll be talking about today, and determining the relationship between those radar variations and other geologic landforms. But I'm also working very closely with a graduate student of mine to do a morphologic or radar morphology map of the surface of Venus, categorizing these tessera and looking at their patterns and how they're related sort of within and between different tessera deposits. So I've said tessera a lot. For those of you who aren't familiar with it, I wanted to just give a definition here, which is that tessera are heavily deformed materials that have a high radar backscatter. So what does that mean? So that tells us high radar backscatter. When we look at a synthetic aperture radar image, tessera appear bright. They are very rough. Because they're highly deformed, there's a lot of ridges and other tectonic structures. And so the radar energy can bounce off of all of those surfaces, and there's a higher probability that that energy will travel back to the spacecraft and be measured. And so we get that high or brightness in the SAR data. I also mentioned previously that they are covering about 7 to 8% of the surface, and they're typically located at higher elevations. And there have been tantalizing measurements of composition to suggest that maybe they are silicic, which is why I refer to them somewhat, maybe controversially, as Venus's continents, the title slide here. But here, I'll just remove that text. So this is what tessera look like. For those of you who are not familiar with radar data, this might give you a little bit of a headache. I definitely crossed all the time when I'm looking at tessera. So this is a series of ridges and peaks, and there's some graben over here as well. You can see kind of light and dark pairing of features. This might be a really good example of a graben right there. But you can see these different slope faces, sort of short slope faces and really long slope faces all throughout the tessera. So they don't all look like this, but generally speaking, this is what they look like, and they appear quite bright. But there's a lot of outstanding questions about tessera, which makes them really fun, in my view. So we don't know how they're formed. They could form from downwelling of the mantle materials, or some people think they could be the result of upwelling. There's also other hypotheses as well, that maybe they're formed due to crustal underplating, or even large impact basin scale impact events. But still no agreement. We also don't know their composition, as I mentioned before, and it could be basalt, it could be granite, it could be something in between. And so many people have been proposing, based on morphology, that they might be basaltic, but there was a European Space Agency mission in the 2000s that measured emissivity, so the amount of energy coming off of a surface around 1 micron, had pretty low resolution. It wasn't really made to make observations of the surface, but it found that there's evidence for a silicic composition. But, you know, tessera don't all have to be the same either. They could be intermediate in composition. They could be sedimentary is another proposal out there. So there's really a huge range in possibilities. So this is just an example of the European Space Agency data. Just on this graph here, I'm showing emissivity versus wavelength. I mentioned that most of the observations of the surface of Venus are around 1 micron because that's where an atmospheric window is located. And these blocks, these rectangles, represent areas that are measurements of the surface. And what they've inferred is that these measurements are more consistent with spectral observations of the kind of microcline quartz and anorthite for the tessera, which is this gray box, and that other materials which are known to be or suspected to be basalts plot closer to the olivine and pyroxene spectra here. But, you know, I mean, you can see the data here, so there's a lot of wiggle room. And then most of these data were collected of the southern hemisphere. And so the hatched regions in this left-hand side image are tessera, and they're lower, and lower emissivity is equated with these more silicic compositions. So these are just two different studies with this approximate same color scheme, where again, low values in these color stretches represent potentially more silicic materials. So the last thing again, which I'll just quickly go through, is that how old are tessera? And the answer is we don't know. Because there are so few impact craters, like I showed previously on the surface, we can't use craters to accurately date the surface. But we do think that based on stratigraphic relationships, they are at least locally the oldest materials and have a relatively higher density of impact craters compared to the low-lying plains. But there's no real information on the distribution of ages, whether the tessera are all the same age or whether they're a variety of ages. So now I'm going to transition a little bit here to gearing up to share my results. And I wanted to show another close-up view of a tessera deposit. This is Phoebe Reggio. So over here on the right-hand side, everything to the right are these low-lying plains that we think are basaltic. And all this bright stuff is tessera. And you can see that within the tessera, there's a lot of brightness variations. You have this area of Phoebe Reggio on the left-hand side that's quite dark. And then on the right-hand side, you have these two areas of high radar brightness. And so I'm really interested in understanding, are those due to post-emplacement modification? Are those inherent to tessera materials? Are they, related to a certain texture? Like, what's going on with these brightness variations? I also want to recognize that not everybody stares at radar data all the time. So just to orient people, when you have a flat surface, it appears dark in radar data. And the reason for that is that it appears mirror-like. So you have a photon of energy or a radio wave or any surface or any bit of energy that interacts with a flat surface. And if it's flat at that wavelength of the energy, it's going to bounce away in the microwave and radar wavelengths. For a rough surface, you are actually going to have that energy be able to bounce off the different facets of the surface topography and return to the spacecraft. And so because you have more energy returning to the spacecraft, those surfaces appear brighter. So flat isn't generally interpreted as, dark is interpreted as flat, smooth areas, and bright as interpreted as rougher areas. Again, at the wavelength of the energy of the instrument. So I'm interested in understanding these slopes. And another thing to keep in mind is that radar data have layover. So all of this, to me, when I'm just looking at it, looks very asymmetric. So this is a ridge, and you have a very long slope on one side, and then this bright thin area here is actually the front slope. So it looks very asymmetric. But in fact, just because of how radar is measured, it could be a very symmetric ridge, or relatively symmetric. So over here, I'm just showing that if you have a small foreslope and a long looking back slope, this is what your brain might see. But in reality, what we're seeing is something that's likely more symmetric. And again, that depends a little bit on the exact sizes and relative proportions and the angle of the spacecraft. But on the whole, a lot of these are much more symmetric looking ridges than kind of what we're immediately interpreting with. So my data are going to be shown graphically for the next couple of slides here. And so I wanted to orient everybody with how I'm doing that. So I'm classifying brightness using a parameter called backscatter coefficient. And so I'll show a couple of graphs where the backscatter coefficient is shown on the y-axis and the incidence angle of the energy on the surface is shown on the x-axis. And we characterize scattering using different scattering laws. And so the Muleman scattering law is a reference for Venus. So I've plotted two versions of this Muleman scattering law on this graph. The important part for me in this presentation is that above these Muleman scattering laws, material is rougher than that average surface classified by that line. And below those lines, it's smoother. So I'm really interested in classifying tessera based on roughness, whether they're rougher than average or whether they're smoother than average. And so here are my results. Just show you them up front. This is them displayed in map view. But you can see all the tessera, hopefully, are either colorized from this green to red, or they're shown in blue polygons. So blue polygons show the tessera that I haven't mapped. I've mapped 22 of them. And what I want you to just take away from here is that there's a lot of green and a lot of yellow and some red. So there's a spectrum both within an individual deposit as well as between deposits in terms of their brightness. I'm going to take this, I'm going to put it on that graph that I showed you in the previous slide. So here are the 22 spectra, or I'm sorry, 22 tessera with each color representing a different deposit. So again, I have backscatter coefficient versus incidence angle. And what I want, again, you guys to think about is that the position of these dots, these data points on the y-axis is referring to their surface roughness. So values that plot higher have a higher roughness, and values that plot lower have a lower surface roughness. I'm going to take these data, and there's a bit of an incidence angle dependence here, and I'm going to remove that because really, again, I'm just interested in this vertical variation. So that's what's shown here. And a couple of things start to pop out, which are really exciting. So a lot of data are plotting approximately between 10 and minus 10 decibels. But we have a couple of areas, in particular, this purple data, which have a very large range in values, with a lot of those values actually plotting high, which means high roughness. So if I take a look at Thetas, which this is the name of the deposit represented by these purple dots, Thetas occurs at high elevations. So this purple box is showing the location of the data on the previous graph. And these high elevations happen to be associated with observations of low radar emissivity. And this is kind of a whole nother thing on Venus, but at really high elevations, there is this change in emissivity, which you can see represented by all of these green to blue areas. And we think that there is some sort of metal coating that is being deposited on rocky surfaces at these high elevations due to an interaction with the atmosphere. And so in these particular areas, the brightness of the surface is related more to composition and less to surface roughness. But even though we had high values, Thetas might not be unique. It's really hard to tell because it's being masked by this different composition. We have Thetas, and the other area which I have found to be very fun and exciting is this blue area, which is the Hospicehagtesera, and they have sort of the next largest range in backscatter value. So I took a look there. I know that Hospicehag does not occur at high elevation, so that emissivity, that sort of metal precipitation or weathering rind is not present in this location. So what I found is that Hospicehag, which is all these polygons on the right-hand side, is just east of an impact crater called Boulanger crater. It's about 70 kilometers in diameter. On Venus, impact craters tend to have these fine-grained parabolic ejecta deposits. And so the boundary of that ejecta deposit is denoted by this dotted line here. And we see that for Hospicehag, you have very low values associated with materials, those ejecta materials, and much higher values, shown by the warm colors here, outside of that area. And so I took some histograms of those data. So all of Hospicehag is shown in this gray histogram. Those data inside the parabola are shown in black, and those outside the parabola are shown in yellow. So you can see that there is this variation on the order of 2.5 decibels in the average value between these two areas. And that's really important, and I'll get back to that in a few slides here as I wrap up. But I wanted to look at all these data, and there's thousands of data points on here. So what I decided to do is bin them by incidence angle. And so that is shown here. Hello? So that's shown on this slide here. And what I'm showing is the average values. And you can see actually that many of the highest density of data really does cluster around a narrow range of values. So I'll just zoom into that area and show you guys it here. We can still see Thetas right here. But what I wanted to do was take this information and classify based on roughness. And so again, those data that have high backscatter are rougher than average, and those that have low backscatter are smoother than average. And so I decided to start by separating tessera into these two groups. And that's shown here. And the red polygons represent tessera that are rougher than average, and the blue represent tessera that are smoother than average. And you can see there's no real longitudinal or latitudinal variations. There's no association with elevation or size of the deposit. But what I did notice is these areas highlighted in circles are different tessera materials that have been positively associated with parabolic impact ejecta. And so right here, this is that Hospicehag that I was showing a few slides ago. But there are several other deposits where there's evidence that the deposition of impact ejecta is significant enough that it is modifying the surface roughness of the tessera and making these deposits smoother. And this is really important because we are starting to look at the division of these materials, what these materials are. Again, there's a big debate, sedimentary, basaltic, granitic, something in between. And future missions are sending, including Veritas, but also Europe is sending the Envision mission, which has the same instrument on it as well. So we're going to be making measurements of the surface rock type, and we need to know whether we're measuring the actual composition of tessera or materials that have been deposited on top of the tessera. So I'll wrap it up here. I don't want to go too long. But I'll just say that some of the exciting results are summarized here, that we see these decimeter scale roughness variations between and within tessera, but most of them map as kind of smoother than average. And that certain tessera have very consistent behaviors where they don't have a large spread in the backscatter coefficient or presumed roughness. And those that have the largest variation tend to be explained either by post-emplacement processes like the deposition of impact crater ejecta, or these dielectric changes. So these, at these high elevations, the low emissivity that is associated with this metallic coating. But in all cases, what we find is that tessera are different from one another at roughness scales on the decimeter scale. But I think most importantly is this message to these mission teams that as we're interpreting that rock type data, we need to be really careful about what we are seeing and take into account these post-emplacement processes. So I'll wrap it up there, and I'll take any questions that you guys have.